Hill Public School online classes. Dear students, grade 11 computer studies is your subject. We are talking about chapter 2, which is encoding schemes and number system. Earlier last week we began about conversion of number systems. We have seen in the beginning how to convert from binary to decimal and from decimal vice versa. Also, we practiced binary to octal and hexadecimals. Okay? We are going to have a quick calculation of some of these exercises today. Also, further we are going to see how to convert fractional numbers. Okay? So without wasting much time, let's begin today. We are going to see 4 conversions. We will have binary to octal, octal to binary, binary to hexadecimal, and vice versa. Okay? So, before I begin, once more, let me give these tips to you. When we're talking about number system, we have 4 number systems. The binary number system, the decimal number system, the octal number system, and the hexadecimal number system. Binary number are always having a base of 2. Decimal number systems have a base of 10. Octal number systems have a base of 18. And hexadecimal number systems have a base of 16. We have to keep these bases in mind because it is these bases we use for calculations during the conversions. We are now going to convert a binary number to an octal number system. Before we begin this, there is a very important point we have to remember. When we are talking about octal, we refer to 2 to power 3. Okay? Octal is 8. So 2 to power 3. When we multiply this, this is 2 multiplied by 2 multiplied by 2. Isn't it? That gives us an 8. So 2 to power 3. This exponent 3 is the number of bits that will represent a binary number in an octal number system. I repeat, when we are converting from a binary number to an octal number, we shall represent the binary number bits according to the exponent of the number system, which in this case is 3. Okay? So, let us finally begin with the conversion. Now, we have a binary number 10, 10, 11, 00, base 2. This has to be converted to an octal number which is going to be in base 8. Don't forget this. The bases are very important. Now, the first thing we are going to do is represent this binary number into bits of 3. Let's begin that. We always start from the right hand side. Okay? Now let's begin representing the first 3 bits 0, 0, 1. These are the first 3 bits. The next 3 bits 1, 0, 1. Okay? And then we have 2 bits more. Now, this seems a little confusing, isn't it? We said we have to represent in bits of 3. We have 3 bits here, 3 bits here, but here we have just 2 bits. What is the solution to that? Let me tell you. Whenever there is a bit missing, the simple thing we do is add a 0 here. Now that completes it in the bits of 3, right? So, whenever the bits are less, if it's not complete, the 3 bits, we add a 0 to it. Okay? Now let's convert this using our conversion table. This is a standard conversion table. Here we have the decimal numbers and this is the converted binary form of these numbers. Okay? We shall make use of that table to convert this into an octal number system. So let's start the first one. We have 1, 0. Now 1, 0 in the conversion table is the number 2. We have 1, 0, 1. Now let's find 1, 0, 1 has a conversion of 5. So we write a 5 here. And then we have 1, 0, 0 which is a 4. Okay? So we have our 4 here. See? We divided this binary number into 3 bits representation. After that, we converted them back to decimal numbers. The result we have here, which is 254, Now, we will be given this number 705 base 8. We have to convert this to a binary number. How do we do that? As simple as this, we have 7, 0 and 5. We take the conversions from the converting table and convert them here. You understand? Now let us see. We have a 7 here, we have a 0 and we have a 5. Now let's see what is the conversion of 7. 7 is 1, 1, 1. Okay? 0 is 0. And the third digit, which is a 5, 5 is 101. Okay? So, we have 7, 1, 1, 1. 0 is a 0. 5, which we saw is 101. But there's something missing here, right? It's the 0. Remember we said that the representation has to be in 3 bits. What do? We add 2 extra zeros. Okay? We add 2 extra zeros. That makes it a complete 3-bit. So, this results in 1, 1, 1, 0, 0, 0, 1, 0, 1. Now, this is our new number in binary number system. So, from a binary, we convert to octal, and an octal number converted to binary number system. This is the methodology for this. Now let's look at another type of conversion here from binary to hexadecimal. Okay? Now we know that hexadecimal is always in base 16, isn't it? So how do we convert this? We apply the same methodology that for 16 it has to be to power 4. So the exponent 4 here is going to represent the number of bits in which this binary number will be represented. Let us do that first. We are always going to start from the right hand side, and if we have bits missing, we will add extra zeros to that. So let's take the first 4 bits, 0, 0, 1, 1, okay? Then the next one, 0, 1, 0, 1, and then 1, 0. So you can see we have 4 bits here, 4 bits here, but only 2 bits here. What is the solution to this? Add 2 zeros. Why are we adding these 2 zeros? So that the 4 bits will be complete in each set. Okay? Now the next thing we do, we convert these to the decimal form using our conversion table. So we have 1, which is a 1. We have 1, 0, 1, 0. Now 1, 0, 1, 0 is a 10. And a 10 in hexadecimal is denoted by the alphabet A. I told you this in your first class that in hexadecimal 10 to 15 is denoted with A to F, isn't it? Keep revising until you remember it. So 10, which is 1010, has a denotion of A. You can write 10 here, but we are converting to hexadecimal. So it will be preferable if you write a here. Okay? We know that A stands for 10. Now the next one is 1100, which is a 12. And a 12 can be denoted with a C. So we write a C here. Okay? We first divide the binary number into a 4-bit representation. After that, we convert them using the conversion table. Now, the result we get, which is a 1, A, C, is our new number in the base of 16. Now, this is the conversion from a binary number to a hexadecimal number. Okay? Now, let's do the reverse of this, which is a hexadecimal number back to a binary number. It is going to be the same methodology. The way we converted from binary to decimal, we will do the reverse now. So, the first thing we do, we are converting this now to a binary number system in the base of 2. So, the first number we have here is a 2, then we have a 3, then we have a B. Never get confused when you come across alphabets in this, okay? Because in the conversion table, I have mentioned this to you and I have provided a table for you. 10 is an A, 11, B, 12, C, 13, D, 14, E, and 15 is an F. So whenever these alphabets appear, do not be confused. Rather, convert and check the value. Okay? So now let us see the conversion here. A 2 stands for 1 0. A 3 stands for 1 1. A 13 will stand for 11 0 1. Let's try the conversion. 1 0, 3 is 1 1, and a D, which is a 13, will stand for 1 1 0 1. 1 1 0 1. Now what is missing here? Yes, bits are missing here because we want a 4-bit representation. So what do? We add zeros for that. Okay? We add zeros so that the bits will be complete. Now look at the answer we received. We have 0 0, 1 0, 0 0, 1 1, 1 1, 0 1 in the place of 2. I hope that's not confusing. After 12, we have 13, which has a binary value of 1101 and is equivalent to D. Okay? This D we have here is equivalent to a 13. And that is the value for it, 1101. We can see when we were converting from a binary to hexadecimal, we had to add 2 zeros to complete the 4 bits. The same way, we had some missing bits here, so we added 2 zeros here and here to complete the 4 bits. And this generates our new binary number system. So this was the conversion from binary to octal and vice versa, binary to hexadecimal and vice versa. Okay? I hope this is understandable for you and easy to use for your further calculations. Thank you.